Hello everyone. In today's lecture, we'll be discussing the stability theorem, the Lyapunov stability theorem, and also we'll have examples and the MATLAB simulation for an example. Here, first we'll state the Lyapunov stability theorem. Let's consider a system described by for a system described by x dot equal to f of xt, and this is function f of xt satisfy for 0 states. It means where f0t, f0 for all t greater than equal to t naught. Now, if there exists a scalar function vxt, which is a continuous partial derivative having partial derivatives and satisfy the following conditions. The conditions, first condition says vxt is positive definite, and second condition v dot xt is negative definite. Then the equilibrium point let's say xc is uniformly asymptotically stable. So for a particular system, we'll consider a positive definite function, and if the time derivative of that positive definite function is decreasing over time, then we can say the equilibrium point, which is basically origin for the system, will be uniformly asymptotically stable. So now let's take an example and validate this theorem. Example: study the stability of the system given by x1 dot equal to x2 minus x1 square plus x2 square, and the second system x2 dot equal to minus x1 minus x2 x1 square plus x2 square. So this is basically a natural system, and we'll study the stability of this natural system, and based on that we can conclude that whether the system should be controlled or not. So at last few lectures, even this lecture also, we are talking about the stability of the natural system. Now we'll find the equilibrium point for the system. Equilibrium point for this particular system equilibrium point will be 0, 0. We can easily find. We have done a lot of examples in our previous lectures how to find the equilibrium point. Now, here we'll find a positive definite scalar function. So here we'll choose, let's choose a positive definite scalar function Vx equal to x1 square plus x2 square. So it is basically randomly chosen, but if you choose any other function, and if you're choosing any other function, but this condition should satisfy. We have chosen this function, and this is also positive. This is basically positive definite function. Now we'll take the time derivative of this function and we'll validate the second condition. So here, taking time derivative of Vx, we can write dou V dou t, V dot xt, we can write dou V dou x1, x1 dot, and dou V dou x2, x2 dot. And from this, we can write from our positive definite function, we can use this formula here. So we can find dou V dou x1, we can write 2x1, and x1 dot already we are having. So we can write x2 minus x1, x1 square plus x2 square. And for the second part here, we can write plus 2x2, and x2 dot already we are having, minus x1 minus x2, we can write x1 square plus x2 square. And from this, we have the expression minus 2 x1 square plus x2 square. So from this expression, it is clear that v dot xt is negative definite. Now we'll check how the system going to behave at equilibrium point. So at x1, x2 equal to 0, we can find v dot 0t, we can write it is basically 0. So we can say at equilibrium point at 0, 0, it's 0, and for at other points, it is negative. Negative at all other points. So the stability theorem, it is satisfied for this particular example. For this particular example, it is satisfied. So we can write according to Lyapunov theorem, the equilibrium point which is basically 0, 0, is asymptotically stable. And also at x for any other value, which is maybe, let's consider infinity, we can say Vxt also goes to infinity. So hence we can write the equilibrium state of the system defined by equation. Let us define, this is equation 1. So equation 1 is asymptotically stable in large, because we are taking the large values of x1, x2. So this is how we can study the stability of the system without solving the equation. This is very powerful tool to analyze the system. Now we'll take another example and we'll find the MATLAB simulation for that particular system, and also we'll comment the stability of the system. Example 2. Consider a system described by x1 dot equal to minus x1 minus x2 e to the minus t, and x2 dot equal to x1 minus x2. Study the stability of the above system using Lyapunov's theorem. So here, similar to the above example, first we have to find the equilibrium point of the system. Solution. The equilibrium point, let us define the equation number 2. The equilibrium point of equation 2 yields to be x1, x2 equal to 0, 0, 0. Now let's select so we have the equilibrium point now. Now we'll study the stability of the system at the equilibrium point. For that, first we have to choose the Lyapunov function. So let us choose a positive definite function, which is nothing but the Lyapunov function, p xt equal to x1 square, x2 square, 1 plus e to the minus t. This is the function we have chosen, but if you want to choose, you can choose yourself, but the condition needs to be satisfied. It should be positive definite. Now from this function, we can easily see that vxt is always 0 for all x not equal to 0. Now we'll find the derivative of this function. For that, we can use this dv dt, which is nothing but v dot x of t equal to, we can write dv dx1 x1 dot plus dou v dou x2 and x2 dot. And from, if you substitute the values in this equation, we have minus x2 square e to the minus t plus 2x1 x1 dot plus 2x2 x2 dot and 1 plus e to the minus t. Now you will substitute the expression of x1 x1 dot and x2 dot in this equation. So let us define this, the equation number 3. Now substituting equation 2 in equation 3, we have dv dt equal to minus x2 square e to the minus t plus 2x1 minus x1 minus x1 minus x2 e to the minus t and plus 2x2 1 plus e to the minus t and x1 minus x2. And if you further simplify, you can write minus 2 x1 square minus x2 square e to the minus t minus 2 x1 x2 e to the power minus t plus 2 x1 x2 plus 2 x1 x2 e to the minus t minus 2 x2 square and minus 2 x2 e to the minus t. It should be squared. And from this, we can write further minus 2 x1 square plus x2 square minus x1 x2 minus 3 x2 square e to the minus t. So from this expression, we can write, okay, we'll take the exponential part because in dv dt exponential part is exist there. So here as t tends to infinity, we can write e to the minus t goes to 0. That is obvious. And using this condition, we can write dv dt, how the energy going to decaying over time. So if you take the time tends to infinity, we can write minus 2 x1 square plus x2 square minus x1 x2. And from this, we can write further minus 2 x1 square minus 2 x2 square and plus 2 x1 x2. Or we can write minus x1 square minus x2 square minus x1 minus x2 whole square. So if we notice the terms, individual terms for non-zero value of x1, x2, these are positive basically. These are positive. So whole values of dv dt is negative. So now we can write, so hence we can write dv dt is less than 0 for all x1, x2 not equal to 0. So from this we can write, hence the equilibrium point, or we can write simply the system is stable basically. We can write as the system is stable. And here further, if you do more simplification, you can write on v of xt, you can write also further, we can write the norm of x, which is x1, x2, we can write x1 square, x2 square, which is also infinity as t tends to infinity. So which implies that vxt equal to x1 square plus x2 square 1 plus e to the minus t goes to infinity as at where we can write x1 x2 if they're infinity. So therefore, all sufficient condition of this function is validated. So hence we can write the origin, which is x1, x2 equal to 0, which is equilibrium point also, is asymptotically stable equilibrium point. Equilibrium point. So this is basically the same way what you have done for the example 1. What you have done here, the same properties also we have followed for the example 2. Now we'll see the MATLAB code for this example, and we'll see whether the system goes to equilibrium point, which is 0, 0 or not. So we have the code for the system. So this is the MATLAB code for this example. So we can notice that we have chosen 2 states. We are simulating, we have taken the initial condition for x1 10 and x2 5, and we are simulating this code for 10 seconds, and we have used the OD 5 to find the solution of these ODs. This is the function we have defined, and this is the variables to be plotted. This is our 2 first order ODs, and this is basically the plot, how to see the labels in XY. This is basically, these are the MATLAB code. And we can see that this x1 and x2 starting from this initial point, and over time they are going to 0. The system is stable. So this equilibrium point, which is 0, 0 in this for this example, and over time the system response goes to 0. So this system is asymptotically stable, and this is also we have validated through this analysis what we have done in this v dot. It is also found to be the system is stable. Basically, the equilibrium point is stable, and also we can see through this response also. So this is how we can analyze the system without solving the equations, the dynamics of the system. In the next lecture, we'll be discussing how we can find the Lyapunov function. That is very important part. And after that, we'll go to the control design process. Thank you.